cache folks. Welcome to this talk about CDC use case designing an evergreen cache. In case you didn't attend my talk on Monday, I'm Nicolas Fränkel. I'm a developer and a developer advocate, and I'm also interested in change data capture and data streaming. I work for a company called Hazelcast. We have two products. The first one is an in-memory data grid. And if you've never worked with an in-memory data grid before, you can think about distributed data structures. So you have a cluster, several nodes, and you can shard the data, replicate the data, whatever. And the other one is Hazelcast Jet, and I will be using in the demo afterwards, so I won't talk right now about it. Our agenda for today is the following. The first thing is I want to define why do we cache. That's the most important thing in the world. Why do we cache? Then I will go through several options and alternatives to keep the cache in sync. Then I will tell you about change data capture, which is right now quite interesting topic, and about Debezium, which is in the Java world the most used CDC implementation. Then I will show you how Hazelcast Jet embeds Debezium, and I will try to impress you with a demo if the demo gods are with me. So, first thing first, caching. You might have heard bad stuff about caching, that if you actually design your system properly, you don't need caching. That is not really the case. Caching is a trade-off, and the trade-off is the following. You accept to have stale data, data that is not up to date with your source of truth, and you benefit from either like speed or availability. Like speed, if your like the usage you make of your data is like the source of truth is very, very far away, is remote, then it will take time to get the data, fetch the data, retrieve the data. So you prefer to use the local data. You know it might not be in sync, and you return it very, very fast. The other like main benefit is availability. I suppose you have heard about microservices. Microservices are not 100% reliable because it's a distributed system. So if the microservices that you want to use is not available, then it's better to return like stale data than not return anything at all. In this talk, I will be much, much simpler because, well, I just want a simple example. And here is a simple architecture. You have your database, which is the source of truth. You have your application, and in between, you have the cache. And here, everything is perfectly in sync because every time your application writes to the database, it also writes to the cache. So when it needs to read again, well, it can read directly from the cache. The cache is always in sync, and that's the perfect state that you want to be in. Unfortunately, that's not really the case. It never happened like this. In general, there is always a component, a third-party component here that will write stuff to the database, and your cache doesn't know about it. And in general, this is a batch, and in general, it writes to a reference table, so like hourly or weekly or daily, you update your reference table, and your cache doesn't know about it. And so one of the oldest problem in the world is how do we keep the cache in sync with the database? And since we are talking about cache, I just want to define some semantics. You might have heard about this joke that there are two hard things in computer science, naming things, cache invalidation, and off-by-one errors. But even if we remove the third item, there are two hard things in computer science, naming things and cache invalidation. And there is two reasons to remove items from the cache. There is cache invalidation and cache eviction. Those are two different reasons. In both cases, you remove stuff from the cache, but for different reasons. So just let's define it. If you want to design a cache provider yourself, that's generally what everybody has done at some point in his or her career. That's what I've done before. You start with a hash map, you are very happy, that's exactly what you want. And then you realize that the cache is unbounded because you are using a hash map. And you probably want to have a bounded cache because if you have an unbounded hash map, then your hash map will compete with the memory of your main application. It doesn't work. So you need to bound it, to limit it somehow. And that's the first reason why you should use a cache provider, because this is provided out of the box for you. So imagine that you have a limit on your cache, and now you have reached the limit. Now you need to cache a new item. You will need to remove one entry from the existing cache. And this is cache eviction. The exact strategy you will use, there are like many different ones. You have least recently used, least frequently used. You can have priorities. You can have your own custom, whatever you want. But this is cache eviction. Now, cache invalidation relates to the time to live. So when you put an entry into the cache, you will tell the cache, hey, this item is valid for 5 minutes, 1 hour, 2 weeks, whatever. And after this time, you will automatically invalidate this entry. You will remove it. So in both the case of cache eviction and cache invalidation, you will remove the entry. The reason for that is completely different. And the previous code is about cache invalidation. So when you put an entry into the cache, it's very hard to think about the correct time to live. And the reason is the following. Imagine we have a regular system. I was talking about the batch before. Let's say we have a batch that runs every hour to update our reference table. Now, if our time to live is 2 hours, that means that if we start at the same time, like after 1 hour, the batch will run, it will update the reference table, and during the remaining hour, our cache will still be valid, and we will be returning stale data. So we will miss this update. On the opposite side, if we have still our hourly batch, but if we have our time to live of 30 minutes, that means that after 30 minutes, we will invalidate the entries, and we will get the data from the source of truth, which will be the same. So we will waste resources. So you can say, oh, but it's very easy. You just set it at the hour. Yes, but you are forgetting two different things. The first is that the clock, since we're talking about distributed system, they are very hard to synchronize. So you cannot tell it, hey, it will be just at the hour, because on one system, you will have one clock, which might differ by some milliseconds from the other system. And then there will be clock drift and whatever. And the other is you don't put all the entries into the cache at the same time. You will put them over time. So there is no really good way to really make the batch and the cache, TTL, in sync. And whatever way you think about it, you can have an external process. You will always have the same issue if you have a specific frequency. So the only way to do that is to be event-driven. And event-driven means, hey, if nothing happens, then we don't do nothing. But then as soon as the write happened on the source of truth, on the database side, then we need to update the cache item. It seems like to be the thing to do, but how do we implement it? Well, if I tell you about databases and if I tell you about event-driven, you will probably think, hey, let's just use database triggers. And that's a quite good idea. We have done that since ages. Now, there are two problems with this approach. The first thing is that not all SQL database server implement triggers. And then the second issue is that normally triggers, they are used to manage the data inside the same database. Here we want to do something that is completely outside of the scope of the database. We want to call an external process, whatever it is, to update the cache. So for this talk, I did a little research, and I will just copy it to MySQL. And actually, MySQL allows you to do that. Of course, there are a lot of requirements and constraints. The first one is the function must be written in C++. Well, I don't know about you, but me, my C++ days are 20 years over. I only studied C++. I'm not really keen on redoing C++ ever again. But imagine you have C++ expert, perhaps you already are one. Then there are other constraints like, hey, the operating system must support dynamic loading, which might not be what you really want. Then it becomes part of the running server. Well, everything is here. If you are interested, the reference is here. And I even found somebody who was nice enough to write a generic library for that. So on GitHub, you can find these components. And the only thing that you need to do is actually to call this sysexec stuff. So you just add this library and you call sysexec, and then you can do whatever you want. It seems like enough, good enough, but if I put on my architect's hats, I see a couple of issues, actually. The first one is implementation dependent. So it only works with MySQL and no other database. Okay, perhaps there are other ways with database which might be completely different. Well, great. Then it seems like it's super fragile. And when I think about fragility, I think, hey, like if something bad happens in production, who will be the person responsible to handle it? And here it touches every silo of your organization. It touches the developer because there are somebody who developed it. Then it touches the DBA because it runs inside the database, and it touches the ops people also because it's production. So it will be a mess. And if you have done also some trigger in the past, you know that it might be very, very resource consuming. So the current way to look at it is to use something called change data capture. You can read the definition, but in like very few words, if you know about event sourcing, you store the events, and then out of the events in the database, you get the state. So for banking system, for example, you would just like store all the inputs and the outputs. And to get the balance, you will replay them in order and to get the state. This is event sourcing in a few words. Change data capture is the exact opposite. You are still storing the state, but out of the state, you are creating events. And actually, if you've got a bit of experience, you might already have done some change data capture in the past. As soon as you've got some polling mechanism with a dedicated column that you will increment or whatever, then you are doing some change data capture already. Triggers seems to be part of the data capture way of doing things, but right now, like there is something that there is an implementation based on log scanners. So just let's talk about log scanners a bit. You might have come upon this article, Turning the Database Inside Out by Martin Kleppman. And in his article, he mentioned the database abstraction. And in that case, as a developer, you don't care about the exact setup of the database. You don't care whether it's cluster or not. You don't care how many nodes there are. What you are doing is, especially in the Java world, you just use a URL and login password, and you just use it. And the idea is that from the developer's perspective, that is good enough. From the ops perspective, it's probably not good enough, because if there is only one node, you will lose your entire data, or at least the database will be unavailable. So in general, what you want to do in production is you have at least a cluster. And because we are using SQL databases, which were not designed to scale horizontally, then it's probably a leader-follower setup. You have one leader that actually gets the requests and serves the request, the read and the writes. And you have a follower here. And the idea is, okay, now if the leader fails, the followers must get the same state as the leader. So how do we do that? And this is an implementation detail, but how is it implemented is through like a log. So every time that the leader receives a change event, an update, or even a change of a table structure or delete table, then it will write it down in append only log. And then what happens is that the follower will also read the same log. And because both will read the same log, they will apply the same events at the same in the same order. And so if the leader fails, the follower will be in the exact same state. So there is another reason also for this log in case of it's not only replication. Imagine you have a single node, then if your process fails, then when the process starts again, it will read the log. So for data recovery, it might be also a good idea to have this log. So the idea is, hey, what if we add the log? That could be a great idea. So here again, I need to go down to the implementation. Here is a sample MySQL binlog, and you can see that there might be some stuff that you can recognize. You can see an update, where, and a set. There is also stuff that might not be that intelligible to you and something that is completely not intelligible. So unless you've got the Rosetta Stone, it's not going to be super easy. And it gets back to my previous points. This is implementation dependent, this is fragile, and who will maintain and debug it? Because here now we are touching like the same silos as before. And Debezium is a Java library that serves as an abstraction layer for change data capture. It's provided by Red Hat. It's licensed under the friendly Apache v2 license. And the idea at the beginning, at least, of Debezium was, hey, it will run into the Kafka cluster. And then every time there is a change on the database, whatever the database is supported by Debezium, then we will create messages into topics. But Kafka is nice, but in most cases, it's not really necessary, especially in my use case where I just want to update the cache. The idea of the cache is I want it to be very, very fast. And I want the source of truth to synchronize as fast as possible to the cache. So if I put a system in between that will write to disk and read from disk, that's not really what I want. Anyway, as I mentioned, there are already some databases that are supported. Those are connectors. So you just will add Debezium and the connector you want to use, and then you will have change data capture for free. And as you can see, the most common one are already supported: MySQL, Postgres, Microsoft SQL Server, even DB2 if you want to. Also, not only SQL database management system are supported. And here we can see that Oracle is incubating, so you can already, like, I think it's nearing completion right now, so you probably can think about using it even now. As I mentioned, Kafka is not always necessary. So if you value to, your speed, then you probably will use a stream processing engine. There are a lot of in-memory stream processing engine. I will talk about Jet because it's the one I know the most. And the idea is that Jet is distributed by default. It's also licensed under the Apache v2 license. And the idea is that it can read from different sources, it can write to different targets, and in between, you can do transform, it will be distributed by default, you can do enrichment so that if you have like data that sits in the database, you can preload it in memory and the enrichment process will be very, very fast. By default, like Jet is written in Java, so if you are a Java developer, by default, the easiest way to use it is to embed it as a library. And then when you start your Java application, you will also start Jet nodes. There will be auto discovery. They will form a cluster. That is very good to start with. That might not be the best case in like when you start relying on it, because then your application and the Jet nodes, they will compete for memory because they run into the same JVM. So the idea is that when you really want to start getting serious about it, you will deploy a dedicated Jet cluster, and then your application will just be a client of the cluster. And the good thing with this approach is that now you're not bound to the Java world anymore. You can use any of our existing bindings, such as Python, Go, C++, C#, and Node.js. Most stream processing engines define a pipeline in the job, and here I'm using the semantics of Jet. You can, in other worlds, you might have different semantics, but the idea is always the same. The first thing is you will define through code what your pipeline does, so where it will read from, where it will write to, and the steps in between. And when you are ready, you will just perhaps package or whatever, you will send this code to the cluster. Then the cluster will receive it, and it's up to the cluster to like send it to the different nodes so that it becomes a job. And it knows about the topology, so it can send it to the nodes it knows about. Now let's get back to our use case, because now we have all the blocks to finally solve this issue. We still have our application that reads from cache. We still have the database. We still have these like components that work with the cache. Now we don't change any of this. What we will be doing is we will be adding a new component that is completely decoupled, that every time there is a change to the database, it will get informed and it will rewrite this into the cache so that the application will always be reading from an evergreen cache. I've talked a lot. Now it's time for some demo code. Here, I have an application and I just want to show it to you. So this is a pretty stupid application. I will try to run it locally first, just to make sure that everything works as expected. Here, I have no, I'm not deploying, I'm just using the cache locally, and I have no process to change the stuff. So this is a Spring Boot application. I don't think that's the really important bit. And now I will be, no, it's not the right one. I had a demo before, so now I have an issue because I was working on something else. I must stop the other application before. I just need to remove this bar right now. And no, that's the fun of the demo. I will check if I have something working underneath GPS. No, it doesn't seem like so. So why am I having this stuff? And perhaps I won't show it locally if it doesn't work. Yes, I had a problem of cache. I don't know why. Okay, so the browser cached the previous application. So here, it's a Spring Boot application. I preload data, but that's not the important bit. The important bit is here what I'm changing. One row, I will update it. And what I will be doing, I will be using the pattern post redirect get. So I will do the post with the data that I've changed, and then I reload the entire page. Works pretty well. That's done. Now, the fun part is I will be using a Docker Compose. And here the Docker Compose is composed of multiple parts. So the Evergreen Cache app is the app that I've just shown you. The pipeline is, well, the pipeline that will read from the database and update the cache. And here the management center, I won't talk about it. It's a dashboard to manage Hazelcast. And here I have MySQL. So here I can start the Docker compose file, Docker compose up. Meanwhile, it will be created. And what I'm doing is, in order to show you how wrong it can go, I will be stopping the pipeline nodes. Stop pipeline. It's Docker compose, not docker compose. Okay. And it should be ready. Yes. Okay, so now it's the same, but now I'm ready and I'm using the MySQL, I'm using Docker, I'm using everything. And of course, I can still do the same stuff. Great. Now, however, I don't have a batch, but I have an application that I can use to change the DB states without the cache being updated, which is the default behavior. So what I can do, I can check the state here. Johnny, Jen, and John, which is basically what I just did. So it's really what I'm reading from the database. And now I can update the third row for the first name to be Robert, for example. Yes. Now if we refresh our application, it's still John. That's not great. And if we do Jenny here, it's still John. So now our cache is not in sync. And of course, we would be able to overwrite and without knowing that Robert would be overwritten because we still think it's John. So it's not the greatest way. So what I'm doing now is I will start the pipeline again. And meanwhile, I can show you how it looks like. And here, the pipeline. So it's a simple Java application. It's a main. I'm not using any framework, nothing. And the really heart of the method, the core, is here. So here I'm creating a new Jet instance. So the job itself and the nodes are completely the same. It's the embedded modes that I showed you before. Again, in general, you would have a deployed cluster. You would send the job to it. Here I'm doing like everything is self-contained just for demo purposes. And I create the pipeline, and the pipeline looks like this. And it reads like plain English. You read from the database. I don't care about the timestamps. I will peek so we can see the stuff in the log. And then you map to a person, and then to a map entry, and then you write to the cache. So the database itself, what method it is? Well, it's like only configuration. Like we already provide as an API all the blocks that you need to read from MySQL binlog, through Jet, through Debezium. You don't care. You just set the database address, the ports, whatever. So it's just configuration. How do we write to the cache? Well, likewise, is only configuration. We just need to tell, hey, which Hazelcast cluster do you want to connect to and the map's name. And in between, you've got the map. So here you will get a change record. We map that to a person, and then we map it to a map entry. So because we want not only the person, but to have the key and the value. Now everything should be set. We can check in the logs that here. I don't see anything right now. Yes, here we can see that the changes were already streamed. So we did some changes, and then we started the job, the streaming job, and it was able to get those changes that happened before it started. So now if we just reload, we see Robert is here. So we were able to update the cache. And of course, now if we do some changes, like again, now it's even better, update to and Caroline. Now, of course, the changes are streamed like right at the correct moment. And I believe that's all that I wanted to show you. So some recap. In this presentation, I showed you about the caching trade-off. Caching trade-off means, hey, I accept stale data and I want either availability or speed. Well, with CDC, you are able to bypass this trade-off because then you don't need to accept stale data all the time. The implementation that I've shown you is through Hazelcast Jet that embeds Debezium, that embeds whatever connector you want, MySQL, Postgres, whatever. So thanks for your attention. You can read my blog. You can follow me on Twitter. If you are interested about CDC to go more in depth, because perhaps I was a bit too fast, we have a tutorial for that. If you want to see more of the code is on GitHub here. So I will be very happy if I receive pull requests or improvements or whatever, or just 1 star. It will be fun. And if I got you interested in Hazelcast, then I would encourage you to join our Slack, or if you are shy, just get some training and afterwards join our Slack. So thanks a lot for your attention. And now there is time for some Q&A if you have questions.